Hello everyone, welcome to OpenFOAM tutorial brought to you by Paanduv Applications. Paanduv Applications provides scientific software development and consultancy in the field of computational physics and AI. Now today let's simulate our first CFD problem using OpenFOAM. So I hope you have installed OpenFOAM in your computers or laptops, and if you have not installed it, you can see our last video with the title how to install OpenFOAM in Ubuntu. So in this video we will run our first simulation. So for first simulation I have created this tutorial folder, and if you have installed OpenFOAM, when you will go to other locations and computer, you can find folder opt. In this opt folder we can see that we have installed OpenFOAM 11. So in this directory we can see the most useful folder for us is the tutorials folder. Inside this it contains a wide range of tutorial cases to help user learn how to set up and run simulations. So in this tutorial we will run a simulation which is based on incompressible fluid. So inside this we will simulate wind around buildings. So we'll copy it from here and paste it where we want to run. We will copy it from here and paste it where we want to run. So we have tutorial, we'll paste it here. Also in the opt folder you can also see the doc folder. In this we can find the user guides, so you can also study these user guides to get a brief overview about OpenFOAM. Okay, so let's go to our tutorial, and we can right click here and open it in terminal. And for starting OpenFOAM, we'll need to set the environment to OpenFOAM. So as we have installed OpenFOAM version 11, so we'll type OF11. Now we are in OpenFOAM environment, and one of the most common commands in Linux is ls, which is also a case sensitive command. If we type ls, we can see it will list all of the folders inside the folder, and as it is case sensitive, capital ls will not work. And to go into this folder we will use cd and wind around buildings. So we have switched our directory to wind around buildings, and if we want to go back to previous directory, we can easily use cd double dot. We'll come back to our initial directory. So let's again go to wind. Now if you type ls, you can see the basic OpenFOAM directory structure. So in OpenFOAM we have a fixed directory structure in which we always need to have three folders: 0, constant and system. So the 0 folder contains the initial and boundary conditions related to your case, like we can see here. Here we can define our like pressure, velocity, and these are related to your turbulence, epsilon, k and newt. And constant folder contains your phase properties, physical properties and momentum. Like we can also have in some cases the gravity. If we want to define gravity, we'll define it here. And when we will have done meshing, so we will also have here a directory named polymesh, which will contain the mesh details. And the system folder contains crucial files necessary for setting up and controlling simulations. And the most important are these three: control dictionary and finite volume schemes, finite volume solution. So control dict defines various parameters controlling the simulation, such as time settings, tolerances, and output control. And FV schemes file contains numerical discretization schemes used for discretizing the partial derivative equations. And FV solution file contains settings for linear equation solvers. After solving the partial derivative equations, we will have some linear equations. So for that we will use FE solution. Okay. So for running our tutorial, system folder also contains block mesh dict, and here it has snappy hex mesh dict. These are necessary for the meshing. And in constant we have geometry. So here our geometry is given in tutorials. Sometimes it is not given in the tutorial itself, it is given in the opt and tutorial folders. There we can find a folder named geometry. As you can see here, tutorials and resources, geometry. For many cases the geometries are given here, but we have it here itself. So in geometry we will extract it here, and we will copy the geometry, and we'll create a new folder here with the name try surface. And the case sensitivity should be the same, and inside try surface we will paste it here, buildings.obj. Or what we can do, like we can also use the Linux commands to do this operation. Like if I delete it, and in terminal we have this. So I will change my directory to constant. Here inside geometry I have my obj file, which is my geometry itself. So I'll make a new directory with mkdir, and name of directory will be try surface. So this command created a new folder inside my constant folder named try surface, as you can see it here. So now I have to copy .obj file to the try surface. I will use cp, means copy, and geometry. Inside geometry I have buildings.obj, and I will paste it under try surface. You can use command, you can use tab button to complete the words. So now as you can see, I have buildings.obj in my try surface. So in this we will use snappy hex mesh dict. For that we will have to create a background mesh, and for background mesh we will be using block mesh dictionary. And in block mesh dictionary it will be a like keyword which will be the background of the geometry. Like the block mesh will create a tetrahex mesh, which should be such that it captures the complete geometry. And also, like, let's see our object, our geometry. So we can use parafoam command. Through parafoam we can open paraview. It will open the paraview. So here I can click on here, and under try surface I have my geometry. So after clicking on apply, you can see this is our geometry. So there are a few buildings, and we will have some airflow like from this direction, and in information we can see the coordinates like bounds. You can see x is from 8 to 237 and y and z. So block mesh dict should be such that it bounds the complete geometry, so it will be greater than this. Like you can see, you can say that these buildings are an car or something, and block mesh dict is a wind tunnel inside which we will have wind flown. And so if you open block mesh dict, we have these coordinates defined, like x minimum is -20 and here we have +8, so like it will be somewhere like that. Okay, and x max is 330 and we have x max as 237. And after defining these, these are 8 vertices of a cuboid, like you can name it as 0, 0, 1, 2, 3, 4, 5, 6, 7. So then this is an order. I'll be showing a picture here which will show the order. It should be such that like the backward face is coming first and then the forward face. Here you can see an picture for the representation, and for boundaries, we will define some patches like 0374 face number. So it always follows the right hand thumb rule. So the vertices should be named in right hand thumb rule order. So here we have defined, like it's the by default tutorial case. If you just want to run your simulation, you don't need to change any of that. Okay, and in control dict we can see we have data related to a simulation, like start time at 0 and time at 400, and it will write at intervals of 50. And you can see here it is form run application, and incompressible fluid is the case. In pulse rate is like how many last time steps you want to have. If I set it to 1, so it will delete all of the intervals except the last interval. And in FE schemes we have data related to the discretization. So you also don't need to change any of that until and unless you know what you are doing. And FE solution we have thus in FE solution we have settings for linear equation solvers, like relaxation factors and equation. Like relaxation factor, it will be such that like based on iterations, like in new iteration how much value of previous iteration the solver will use. And in snappy hex mesh dict, you also don't need to change any of this. We will create another video based on which will explain block mesh dict and snappy hex mesh dict. And surface features extract is we are using this for extracting the features from the geometry. So now under constant folder we can see momentum transport. So momentum transport contains properties related to turbulence. We'll be using the RAS turbulence model, and inside RAS we will use K epsilon model. We can, if you don't want to use turbulence, like we can remove it and then type laminar. So in that case it will use laminar model, so we are not changing it right now. And in physical properties it contains nu is the kinematic viscosity. And under trisurface we have buildings.obj that we defined, and in 0 folder we have initial and boundary conditions, like epsilon, k and nu t will be related to our turbulence. So like if I open epsilon, so you can see dimensions for epsilon are here, and we have initially defined value of epsilon, and like in block mesh we have created patches, inlet, outlet and wall. So at inlet we will define as fixed value, and at outlet we are using inlet outlet boundary condition. So these are the boundary conditions, and this is the initial condition. And like for pressure we can see we are using 0 gradient at inlet, and at outlet we are using total pressure boundary condition. And for the internal field we have defined uniform 0 pressure. And in velocity we have defined inlet velocity as 10 meter per second, and internal field we have defined 0. So in the boundary field now we can see that at inlet patch we are using fixed value boundary condition, and the value we are defining it by uniform $u inlet. U inlet, like it is a variable that we defined, and all of these are in C++ structure. And at outlet we have defined pressure, inlet, outlet, velocity. So you also don't need to change any of it right now, and like we are running this tutorial just for a trial. So now let's run it. Like our paraview is open, it is saying for that, and I will close it from here. So firstly we will use surface features. It will भैया करना बंद रोक दो. So as you can see that surface features has given an error, and the error says cannot find file. It is searching under constant. So like our current directory was the constant folder, so we'll have to change our directory to the main keys directory. So we'll use cd dot dot, and using up arrow we can go to previous commands. So again I will learn surface features. So now it has extracted the surface features, and you can see here inside constant it has created extended feature edge mesh folder. Inside it this is the edge.emesh we can say. Okay, and under try surface we have our object, and now we will run block mesh, which will create the boundary mesh for our case. And block mesh is created. I'd like to tell another Linux command which is touch. Touch is used to create new files, so we will create touch simple dot form, or we'll say building dot form. Dot form is the OpenFOAM case structure which we can open in paraview. So it will create a file named building.form in our case directory. So here you can see that, and you can also use like paraform. It will create a temporary .openform file, and which will open in paraview. So here you can see this is the block that has been created with the block mesh, and if we click in surface with edges you can see it. You can make it more refined using the block mesh dictionary. We'll explain it in later videos. Okay, so now I'll say I'll close it and we'll clear our terminal. Our work will be still saved. Clear will just clean the terminal so it will look more clean. Now I have run the block mesh and now we will use snappy hex mesh. Snappy hex mesh. So it will create a mesh inside our block mesh and outside our buildings. I forgot to tell you earlier. In snappy hex mesh dict we have the inside point. So this point needs to be defined like this point we have defined such that it is inside the block mesh but outside the our like geometry file, which was the .obj file. So it is outside the buildings. So the mesh will be created on the buildings and inside block mesh. If this point was defined inside any, like inside the geometry, it was an inside point of geometry, in that case the mesh would have been created inside the geometry, so that would have been of no use. So snappy hex mesh, we are currently running it in serial. We'll tell in later videos how you can run your cases in parallel. I'll use snappy hex mesh minus overwrite, which will overwrite the cases, and here you also can use T to write the log file. So now it has started to create mesh.
A few moments later.
So you can see that the meshing has been completed within a minute or so, and if I had more refined mesh, it would have taken more time. So to view the mesh, we can again use parafoam. And if you can try to reduce the opacity, you can see we have now buildings created. And if I click on surface with edges, you can see this is the final mesh. Okay. Now we can check the quality of mesh. Now we can check quality of mesh using check mesh command. So you can see like it is saying mesh okay. You can read about parameters also. We have done like geometry preparation. Geometry was already there. We have done the meshing part. Now we will run the solver. So for solver, you can see in control dict we have foam run. This is the application. So we will have to type foam run to run our application. And if I enter, the case has been started. So it will take some time.
A few minutes later.
So guys, you can see it took around 6 minutes for the complete simulation. Now we will visualize it. Now we will visualize it in post-processing using ParaView. We can again use parafoam and apply. So now we can see velocity, and you can see here that we defined at inlet 10 meter per second. So at inlet patch we are having complete 10 meter per second velocity. And now let's reduce the opacity, and for viewing the velocity we will be using stream tracer. It will show streamlines across our domain. We'll use a point cloud and we'll increase its radius like 200 or something. Oh, now yeah, it is capturing complete. And if I click on apply, so after reducing opacity we can see our case, and we'll go to our last time step. Now you can see that this is the weak part after the air has flown through the buildings. And now we will visualize it using streamlines. We will use this tool stream tracer. You can directly click it from here, or you can go to filters and then you can use search filter, and we'll use stream tracer. And you can use line, or you can also use point cloud. I'll use point cloud with 200 radius. It will capture the complete domain. And if I click apply, and if I hide it, you can see some streamlines. We can change the color of it also, like from here. And I like rainbow desaturated, so I'll hide this sphere also. Like now these are the streamlines, and we can also load our obj file so that we can see it more clearly. So yeah, now you can see the wind is coming from left side and some turbulence is being created here. And if I can increase the resolution, yeah, like if I increase it to 1000, the number of streamlines will be increased. And now you can see it is quite cool to view. And on stream tracers we can also use another filter called tubes. And if I click on apply, it will be very large first, and I can reduce the radius. So yeah, and now you can see like the wind is coming from this and how it is flowing over the buildings, and you can visualize it the way you want. And there are many filters and tools in ParaView. And on our main file I can also create a slice, and along the Y normal, so you can see this is the building outline and how the air is flowing. I can also plot some vectors on it, like this will be orientation will be along velocity, and I'll scale them so that the size is maintained. And now you can also see how the vectors are looking. And if I plot it as all points, you can see like some recirculation is also being created. You can post process it the way you want.